It's March 2016, and this is Wow Signal Burst 13, Tabby's Star for the Perplexed, Part 1. For more information, please visit wowsignalpodcast.com. Hello, this is Paul Carr. When it comes to Tabby's star, we are all perplexed. This burst is for those of you who are disinclined to read technical papers by professional astronomers, but would like to know just what the heck is going on. What is all this stuff about alien megastructures, swarms of giant comets, and old photographic plates? We'll lay that all out here for you. In part 1, we will talk about why Tabby's star is perplexing. And in part 2, we'll talk about some of the theories that have been proposed for Tabby's star and why they don't fit or why they might fit. But essentially, no one knows at this point what the answer is, why this star is behaving the way it does. First, a few basic facts we should all know. Stars vary quite a lot in size, brightness, and temperature, but most are small and relatively cool and burn for billions or even tens of billions of years. A smaller population of stars are like our own Sun, which is called a G-class star, and some stars are even bigger and brighter than the Sun. Tabby's star, an informal name, it's known in some star catalogs as KIC 8462852, is one such big bright star, is called an F-class star. A bit bigger, quite a bit hotter, and considerably brighter than our Sun. It is just under 1,500 light years away, so we are seeing as it was not quite 1,500 years ago, and is in the constellation Cygnus. Stars are born in a collapsing cloud of gas and dust. They burn steadily for a while, and then they die. While they are burning steadily, they are called main sequence stars, and when they die, they change size and color and can vary quite a lot in brightness. Astronomers can study the light from a star and determine the approximate age, just as your vet can tell how old a cat is by looking at its teeth. Tabby's star is neither very young nor very old. It is a main sequence star and should burn steadily. It turns out that Tabby's star was one of the many stars that the planet-hunting Kepler Space Telescope was staring at for about 4 years, starting in 2009, in an effort to find planets around those other stars, or exoplanets. Kepler is able to find exoplanets because for some subset of those stars it is keeping vigil on, its planets will pass across the face of the star from our vantage point, and we will see a very slight dimming of the star when this happens. Although the resulting variation in brightness is subtle, it should repeat in a rhythm that is a fingerprint for such transits, and this fingerprint can be recognized by careful analysis. More exoplanets have been discovered with Kepler than any other telescope, 1,039 confirmed exoplanets at this writing. Big exoplanets are easier to detect than small ones, and planets close to their star with shorter period orbits repeat their transits more often, and so are easier for Kepler to spot. A problem with the Kepler spacecraft in 2013 meant that it can no longer stare at the same patch of sky that it did at first, so it is no longer keeping watch on Tabby's star. However, the data produced by Kepler continues to be analyzed by astronomers and notably by a group of citizen scientists called planet hunters. The planet hunters study the subtle variations in stellar light curves by eye, augmenting the sophisticated computer analysis used to detect many of the exoplanet candidates Kepler has found, and they flag unusual events in the light curves for follow-up by the science team. In the fall of 2015, a puzzling finding by the planet hunters was reported by Boyajian et al. We'll just call this paper B 2015 from now on. What the planet hunters saw was not just the usual dips in brightness that you find in a star with transiting planets. They found unusually large dips and a complicated set of dips. Plus they found some of the smaller dips that you might see if planets transit, but the rhythm seemed odd. It wasn't like the transits of a close-in planet. So over the roughly 4 years the telescope was staring at the star, they found 2 major groups of big dips. There was a downward spike at around day 800, henceforth called the D800 dip, that lasted a few days, and just after day 1500, the D1500 dip. These are real data, not mistakes, and they are much larger than the normal dips in magnitude observed when a planet transits a star, typically close to 1%. 2 of these dips, numbered 5 and 8 by the B 2015 team, are around 20%, which is only achievable by an object more star-sized than planet-sized. Dips 9 and 10 are also considerably larger than any planetary transit. There are smaller dips as well, and the B 2015 paper identifies 10 biggest events in Table 1 of that paper. Based on its temperature and type, Tabby's star is probably more than 2 million kilometers in diameter, more than 50% larger than our Sun. By comparison, Jupiter is 138,350 kilometers in diameter, so even a large planet would barely cause a dip in luminosity, a few percent at most. Whatever passed in front of Tabby's star was big, the size of a small star itself, and yet no other close star is in evidence. Another important thing to note is the time scale, which you can see for yourself by examining Figure 1 in B 2015. The events took place on a time scale of days, and some of them about 10 days. This is a big part of the puzzle. I would also note something else I don't know how to interpret, but the team found some evidence that a 48.4-day period is involved. Something orbiting at that period would be about 44 million kilometers from the star, which is quite close. Something that close to such a bright star would be hot, with an equilibrium temperature of 1070 degrees Kelvin. If I did my arithmetic right, and it would glow fairly brightly in infrared at a wavelength of about 3 microns. As we'll see, no evidence of an object emitting infrared light around that wavelength has been found. There is a lot of information packed into the 17 pages of B 2015, and on this Part 1 and also in Part 2, and I will try to unpack for you what some of that evidence, but I am leaving out many details and interesting wrinkles. The science team followed up the Planet Hunter's discovery by asking all the obvious questions. Could the data be an error? Are we looking at 2 or more stars instead of 1? Is there something unusual about this star? Does the electromagnetic energy coming from the star give us a clue as to what could cause the dips? It turns out there wasn't a whole lot of astronomical literature on this particular star. There are, after all, billions of stars that telescopes can see, and most have not been the subject of close scrutiny. The first thing they did was check with the Kepler team. Had they seen anything like this before? Could it be something wrong with the telescope or the sophisticated instrument on the telescope's focal plane that measured the brightness of the stars? The Kepler scientists took yet another close look and shook their heads. The data was real and wasn't showing up in other stars' light curves, as you would expect if it were a problem with the instrument. The Kepler scientists could find nothing wrong with the data. They believe the brightness curve, sharp dips and all, is real. The next thing the team did was take a closer look at the data. They tried more sophisticated analysis techniques to try to understand if anything in this complex pattern repeated. They found that there is a strong component at a 0.88-day period, which the B 2015 argues strongly is caused by the rotation rate of the star itself. Other data in the observational follow-up is consistent with this. Some other interesting bumps were noticed in the frequencies, including a 10 to 20 day pulsation, but no one knows exactly how to interpret them. They may just be natural variations in the star's brightness. Boyajian's team followed up the Kepler observations with ground-based telescope observations. An examination of observations with the United Kingdom Infrared Telescope revealed a tiny speck that may or may not be a small companion star. Images from the giant Keck telescope revealed that there is another, fainter star apparently close to Tabby's star, but it is not clear if it is a distant companion or just another star passing close to the same line of sight. Observations were able to rule out a close companion or a bright companion, but it is possible that a red dwarf star circles Tabby's star at a distance. The B 2015 team were mainly interested in detailed analysis of the star's light, using the science of spectroscopy, which is crucial to our understanding of the universe. Spectroscopy can not only tell us what sort of elements stars are made of, but since we know what the light spectrum looks like from laboratory work, it can also tell us how fast that material is moving either towards or away from us. Since the wavelength shift up, away, or down, towards, due to the Doppler effect. Over many generations of studying spectra, astronomers have learned to infer a great deal about a star from its spectrum and measurement of the Doppler effect on it. One thing they learned from the spectroscopy was that the star is in fact an unremarkable star of a fairly bright yellow-white class called F, which constitutes about 3% of main sequence stars. The star appears to be rotating fairly fast with a period of 0.88 days. Compare that to our Sun's 25 days. They were able to estimate the mass and size of the star and determine that it is likely to be neither a very young F star nor very old. It is in the middle of its life cycle. Its brightness should be steady. Now, there are two other things you should know about what the B 2015 team observed, and plus there are some additional follow-up observations that we'll talk about. There were measurements of what astronomers call radial velocity. Now, if there is a large companion to the star, it will cause the star to wobble, moving towards and away from us as the companion star rotates about it. They did not find any clear evidence of any large dark companion. We already know that there's not a large bright companion. So, if there is that companion, it's not consistent with the radial velocity data. However, the radial velocity data is not that accurate. There could still be companions there, just not big enough to cause these kinds of dips in the brightness. There was also something called infrared excess. What the team did was look at existing data from telescopes that are sensitive in the infrared band, which is the wavelengths of light that are longer than our eye can see, but still shorter than radio wavelengths. Now, if some solid or liquid object is absorbing 20% of the light from Tabby's star in our line of sight, it should heat up. And then basic physics says that energy will be emitted in infrared light. So if we plot the energy we're seeing versus the wavelength of the light that we see, then we should see the normal light from Tabby's star and then a bump out in the infrared, or in what are called millimeter waves if the object is far from the star, not getting as hot. The bump is what is called an infrared excess, and the B 2015 looked for one in the space telescope data available to them and with a ground-based telescope. They did not see any excess. The B 2015 team and others looked at the survey data from the WISE Infrared Space Telescope and later followed up with data from the Spitzer Space Telescope and with both an infrared and a millimeter wave telescope on Mauna Kea, and found no clear evidence of anything absorbing the light from Tabby's star and re-emitting it as waste heat. There were some little hints that something might be there in the Spitzer data at 4.5 microns wavelength, but we shouldn't get our hopes up. Where we would expect to see the infrared spectrum peak depends on your hypothesis of how close the star is to the absorber. So, to sum up for you, we have a star is showing dips much larger than any other star seen by the Kepler Space Telescope. A big, bright star that should be just burning steadily. Now, that would make sense if it had a large companion, but there's no evidence that it does have a companion, and it would have to be very large, big enough to be a star itself. While we think there may be a small, dark, red star orbiting a long distance away from the star, it's not close enough to show this kind of pattern that we see in day 800 and day 1500. The other thing about the star is that so far, the research has shown no infrared excess, which means whatever it is that is crossing the star isn't staying hot, or for some other reason, we can't see the infrared waste heat. So that rules out quite a few things, which we'll talk about in the next episode. Now, in part 2, we'll talk about some of the possible explanations for these very large dips in the brightness of Tabby's star, and we'll also briefly mention some research that seems to show a longer-term dimming, although we've already covered that quite a bit in previous bursts and episodes here on the WOW signal. In part 3, we'll talk about some of the more frequently asked questions about Tabby's star, and also cover some of the more exotic explanations that have been proposed. It can get quite fun to think about all the possibilities. So that will be the third part of this. And hopefully by then, will be some new developments to talk about. So please stay tuned and go visit wowsignalpodcast.com for more information and to subscribe to the show so you always get the latest right on your phone, tablet, or desktop. This has been Burst 13 of the WOW Signal Podcast. For more information, please visit wowsignalpodcast.com. The WOW Signal Podcast is distributed under the Creative Commons Attribution Share-alike license. Music by Jason Robinson.